Okay, hello everybody. So today we're going to begin our discussion in chapter 10, section 2. And what this chapter and section covers is how to simplify radical expressions. Now, radical expressions are algebraic expressions that are written that have a square root symbol in them. And so this entire section is going to deal with how to simplify radicals. Now, you may recall the perfect squares. What perfect squares are the numbers that can be square rooted and give you an integer answer. Actually, in this case, it would be a whole number answer. So, as an example, if you took the square root of 16, 16 would be 4. If you took the square root of 25, that would be 5. The square root of 36 would be 6. So there's a list here of the first, 1, 2, 3, 4, 5, 6, 7, 21 perfect squares. It goes all the way up to 25 times 25, which is 625. So those are important numbers to be able to recognize. So as you're simplifying these radical expressions, you may have to utilize this chart in order to have your radical expression in simplest form. So let's take a look at how to do this. So what you see here for the first one is that we have the square root of 8. And the square root of 8 itself is not a perfect square. If you look here, the perfect squares go from 4 to 9. But what can happen with this 8 is the 8 can be broken up into a number that is a perfect square. And with practice, you'll begin to be able to identify what perfect squares are hiding in these numbers and how to take them out. So let me just show you how to do this first one, which is you will break up 8 into 4 times 2. Now, the reason why we broke up 8 into 4 times 2 is 4 is a perfect square. So once we have it broken up, we can then take the square root of each of the numbers individually. And in this case, the square root of 4 becomes 2. And then the square root of 2 is left alone because 2 is not a perfect square. And what you see here is the final, most simplest form of this radical expression. So as you can see, the goal here is to dig out these perfect squares that are hiding in possibly a bigger number and get them square rooted so then they become, or they are shown outside of the square root. So here's another number, 12. And looking through, if you think of the factors of 12, it'd be 1 and 12, 2 and 6, or 3 and 4. Now, 3 and 4 are going to be the two that we use because 4 itself is a perfect square. So I'm going to break this up into 3 times 4. And then you can see I will square root each of these numbers individually. Sorry, this would be a 4. The square root of 4 is actually 2. So what we will have is we'll have the square root of 3 because we can't simplify that times 2. Now, as a general rule, when you write these types of expressions, you want to have the number that is not inside the square root written first. So because multiplication separates these two things, I can multiply them or write them in either order. This is the commutative property. So I'm going to write it as 2 times the square root of 3. And there's the most simplest form of that radical expression. So moving on to 48. 48 is a bit of a bigger number. And these can be a little bit tricky to break up. So I want to show you another way that is maybe a little bit more complicated until you catch on to it. But once you catch on to it for these bigger numbers, I think it's a better way to operate. So what we can do with 48 is we can actually make a factor tree with 48. And we're going to prime factor 48 all the way down to its prime number building blocks. Now I can immediately see that 4 and 8 are both divisible by 4. So I'm going to break this up as 4 times 12, which would give me 48. 48. Now, 4 and 12, neither one of those are prime, so they both can be broken up again. The 4 will turn into 2 times 2, and the 12 will turn into 2 times 6. Now I'm going to circle 2 and 2 and 2 because those numbers cannot be broken up anymore, but 6 can be. 6 can be broken up into 2 times 3. So now that we have it all broken up, we can write this as its prime factorization. So 48, if I did 2 times 2 times 2 times 2 times 3, that will give me 48. So I'm going to rewrite 48 as 2 to the second, because there's 2 of these. And then I have 2 more 2's to the second times 3. Now you'll see why I want to group these as 2 to the seconds in just a moment here. But hopefully that makes sense that we have, this would be 2 times 2, which is 2 squared. This would be 2 times 2. And then we have a 3 that's off by itself. Now here's why we did this. What you need to know is that square roots, these square roots right here, cancel out squared powers. So what will happen is we're going to underline this base, and then we are going to cross out the 2. Then I'm going to underline this base and cross out the 2. Now, the reason why we underline both of those 2's is both of those 2's are going to come out of the square root sign here. So we'll have 2 times 2, and then we'll have a square root, and the 3 will be left there because it did not have a power that got canceled. Now, the last thing to do here is to multiply the 2 2's. That gives me 4 square root of 3. And there is our final answer. So you can see that this way seems to be a little bit more complex, but it is definitely a better strategy for when you have bigger numbers under the radical. Now, looking at the next one that we have, the square root of 6, if you look at 6, the factors of 6 are 1 and 6 or 2 and 3. None of these numbers, none of them, 1, 6, 2, or 3, none of those are perfect squares. Therefore, you cannot simplify this any further. It's just left as the square root of 6. So we have quite a few more to try here yet. So let's keep working through. So here's the square root of 32. I do want to transition into using that factor tree again. So let's draw a factor tree of 32. 32 is even, so we know it is at least divisible by 2, and 32 would be 2 and 16. Now, 16, 2 is prime, so we can circle that. 16 would break up into 4 times 4, and then each of those would break up into 2 times 2. So what you can see now is 32 can be broken up into 2 times 2 times 2 times 2 times 2. Now I'm going to write these as pairs though. So every time I have a pair of numbers, I want to write them like this. So I'm going to break up 32 into 2 squared times 2 squared times 2. So this represents 2 squared, this is 2 squared, and then there's one more 2 that we write right there. Now, why do I write it like that? Well, once again, square roots cancel squares. So in order to get rid of these powers right here, we can cross these out and underline the 2's, just like that. And so the stuff that is underlined will come out of the square root, and if there's anything that did not have a power canceled, it remains behind in the square root. So in this case, we have 2 2's that go outside, and we have a 2 that's left behind. Now, 2 times 2 is 4, and we're left with square root of 2. There's your final answer. Now, for 40, this one might be a little bit more obvious, so I'm going to go ahead and go back to the first way that I showed you. 40 can be broken up as 4 times 10. And I think we can recognize right away that 4 is a perfect square. So if I rewrite this, I have the square root of 4 times the square root of 10. And the square root of 4 is 2. And the square root of 10 cannot be simplified any further. So there's your final answer. Now, you could do the factor tree method with this square root of 40 if you wanted. It just so happened, though, that I recognized that 40 had a perfect square 4 in it, so I didn't need to use the factor tree. And so that's what I would encourage you to do, is that if you could just break it up into its perfect square factors and then simplify it like we did for this one, then you don't need to use the factor tree. But if you have a number that you're not quite sure what the perfect square is that's hiding inside, then you're better off to use the factor tree method. So 27 would be 1. I think you guys should know that 27 can be broken up as 3 times 9. So I'm going to go ahead and break that up into 9 times 3. And then I'm going to individually square root the 9 and square root the 3. As you can see, the square root of 9 is 3. So this becomes 3, and then the other square root of 3 is left alone because you cannot simplify that any further. Now for 75, I don't think 75 is immediately obvious how it should break up. So what I would recommend doing is using a factor tree in this case. So we'll go ahead and write 75, and we'll break this up. 75, we know it ends in a 5, so that means a 5 will go into it, and a 5 will actually go into 75 15 times. Now we'll circle 5 because it's prime, but 15 needs to be broken up further as 3 times 5. Now, what you can see here is that we have 2 5s. There are 2 5s, so we will write that as 5 to the second power, followed by 1 more 3. So it's 5 times 5, and then times 3. Now, why did we write it as 5 to the second power? Well, we did that because square roots cancel squares. So this 5 will get underlined, and we will cross out the 2, and you will see that 5 will come out, and the 3 will be left behind, just like that. Now we'll do a couple more. I got about 4 more for you. So we'll start with this 45. Hopefully you can recognize that 45 is a multiple of 9. So this would turn into the square root of 9 times 5. Now, why do I want the 9? Well, 9 is a perfect square. So that will allow us to square root the 9 and square root the 5. The square root of 9 is 3. And then we leave it as the square root of 5 because that will not simplify anymore. Now for 60, once again, I'm not sure that it's immediately obvious what perfect square is in 60. So we will go ahead and do a factor tree for 60. We know that's 6 times 10. We know 6 will break up into 2 times 3. And we know 10 will break up into 2 times 5. So now I'm going to do this just a little bit different and see if this maybe helps you understand. I'm going to rewrite the square root of 60 as 2 times 2 times 3 times 5. Now when I have these groups of 2's, I can rewrite that as 2 to the second times 3 times 5. Now, just like in the other ones, if we have anything squared, the square root will cancel the square, and we will bring that base out. So I'm going to rewrite the 2 on the outside, but we're left with 3 times 5 on the inside because it did not have a power that canceled. So then the last thing to do would be to multiply the 3 times 5, which gives me 15, and then we now have our simplified radical expression, 2 root 15. So I'll show you 2 more. Here's 54. Hopefully you can recognize that 54 is a power of 9. It is 9 times 6. So I'm going to break this up as the square root of 9 times 6. You can see that we will individually square root each one of these numbers, which will give us 3 root 6. And there's your final answer for that one. Now, the last one, I do not think it's obvious. Maybe it is, maybe it isn't, but there is a perfect square in there. And 500 is actually 5 times 100. 100 is a perfect square. So I will break this up as 100 times 5. And then we will break this up as the square root of 100 times the square root of 5. The square root of 100 is 10 root 5. And there is our final answer. So I hope that made sense. I know there's 2 different ways to do this. You can do it either way. The factor tree method is for when you have a number that you might not know one of the perfect squares in there. You can utilize that method. So we're going to practice this some more. But in the meantime, if you have any questions, feel free to email me. Have a great day.